So let's take a question. A train of length L equal to 350 meters starts moving rectilinearly with a constant acceleration W equal to 3.0 into 10 to the power minus 2 meters per second square. T equal to 30 seconds later after the start. The locomotive headlight is switched on. This is being called as event 1, and tau equal to 60 seconds after that event. After that event means after event 1, the tail signal light is switched on, which is being called as event 2. Find the distance between these two events in the reference frame fixed to the train and to the earth. How and at what constant velocity v are relative to the earth must a certain reference frame move for the two events to occur at the same point? Now this question basically talks about a train with a headlight which is turned on 30 seconds after it starts moving, and that is being called as event 1. 60 seconds after that event means 60 seconds after event 1, the tail signal light is switched on, and that is the event 2. So event 1 happens 30 seconds after start, event 2 happens 90 seconds after start, right? Find the distance between these two events in the reference frame fixed to the train and to the earth. Now if I am inside the train, I will see that the first headlight gets switched on, say 30 seconds after start. If I am inside the train, I will see 60 seconds after event 1 or 90 seconds after start, the tail signal light is switched on. So for me, if I am sitting inside the train or if I am in the reference frame fixed to the train, the only thing that I will see is that event 1 is happening at the head of the train or at the front end of the train, and event 2 is happening at the tail end of the train, right? From any reference frame which is fixed to the train, the difference or the distance between event 1 and event 2 is equal to the length of the train, right? Because in the reference frame which is fixed to the train, event 1 I am able to see at the front end of the train, and event 2 I am able to see at the back end of the train. Now this is another part of the question. Find the distance between these two events in the reference frame fixed to the train and to the earth. Now suppose if the train is like this, say, and it goes here in this direction. So this is the front end, I'll call this is F, and this is the back end, I'll call this is B, and this length we know has been given to us 350 meters. Now we have been told that the train starts moving and it moves with a constant acceleration of 3 to the power minus 2 meters per second square, and event 1 happens 30 seconds after start. So the front end of the train, if you want to calculate how much does it move till from the start, when the train starts moving, from this point to the point of time where the event 1 takes place, how will we be able to calculate that? S is equal to u t plus half at square. U is 0 because it says train starts moving. U is 0, half at square. A is equal to 3 by 100 into t square. 30 into 30, right? This will have some value, 3 into 3, 13.5. So it means that the front end of the train after 30 seconds would have traveled 13.5 meters distance, Now suppose we start to measure the x coordinates from this point where the back end of the train was initially. So if we start to measure the x coordinates from this point onwards, this will be equal to this much, 350 plus 13.5. Why? Because 350 is the length of this particular train, and 13.5 we just calculated here is the total distance traveled by the front end of the train. So the total distance traveled by the front end of the train is this much, and the x coordinates of the front end of the train will be equal to 350 plus 13.5, which is equal to 363.5. This is one thing. Second thing is, if now let's come to the second part of the question. The tail signal light is switched on 90 seconds after the starting of the train and 60 seconds after event 1. Now let us calculate the total distance traveled by the front end of the train in 90 seconds. That will be equal to ut plus half at square, which is equal to how much? This is equal to 121.5. So now total x coordinate of the front end of the train will be equal to 350 plus this, 350 plus 121.5. Now the x coordinate of the back end of the train will be this minus 350, which is equal to 121.5. Right? So the distance between the x coordinate of the back end of the train is 121.5. The x coordinate of the front end of the train is 363.5. So the difference will be 363.5 minus 121.5. It's equal to how much? 242. So in the reference frame fixed to the earth, the total distance between the event 1 and event 2 is equal to this much. Right? I think it's very clear the way it has been calculated. I have first calculated the front end of the train and how much distance is traveled when the event 1 took place. We know that event 1 took place 30 seconds after start. This will be equal to this much. X coordinate of the front end of the train, where you are starting to measure x dimension from this point. At this point you are considering to be x equal to 0. This is the train. This is x equal to 0, this point. So suppose the train has traveled this much distance, this is equal to 13.5. The x coordinate of this point will be this distance plus the length of the train. So this is 13.5 plus this length of the train is 350 meters. We have been given here. So this is equal to total 363.5 meters. X coordinate of the front end of the train. In a similar way, you calculate the x coordinate of the front end of the train for event 2. Simple application of this equation of motion. Ut plus half at square. The only difference is t in for the event 2 is 90. A is the same as in the case of the first calculation that you did. So half a t square, t is 90. If you calculate this, you will get the x coordinate of the front end of the train after 90 seconds. Now you are interested in the back coordinate of the train because that is where the tail light is getting switched on. So x coordinate of the back end of the train will be equal to this minus length of the train. This is the x coordinate of the front end of the train. Distance traveled by the x coordinate of distance traveled by the front end of the train is equal to 121.5. We calculated it. X coordinate of the front end of the train after 90 seconds, SF x dash we are calling it, will be equal to 350 plus 121.5. x coordinate of the back end of the train will be equal to 350 plus 121.5 minus 350, because if this is the x coordinate of the front end of the train, x coordinate of the back end of the train obviously will be equal to this minus 350, which is equal to 121.5. So these are the two coordinates that you are focused on actually. One is the x coordinate of the back end of the train after or during event 2, that is equal to 121.5 meters. The other coordinate that you are considering is this one, SFX, x coordinate of the front end of the train when event 1 has happened. This is equal to 363.5. So the difference between these two will be equal to 363.5 minus 121.5, equal to 242 meters. Okay, I think it's pretty simple the way what has been explained till now. Now coming to the last part of the question, how and at what constant velocity v relative to the earth must a certain reference frame move for the two events to occur at the same point? Now let me draw the diagram of train once again. This time I will depict both the events happening. This is the train and it goes like this in this direction, like this. This is where event 1 is happening, suppose. This is where event 2 has happened. Okay, this is 1, I'm just writing 1, and this is actually event 1, this is 2. Right? Suppose if parallel to this railway track there is another road and there is a car going on this road. Okay, this is the road and this is the railway track. Car moves exactly parallel to the railway track. Now suppose if the car was exactly here, exactly the motorist was also going in this way, and the line connecting the position of the motor of the car and the position of the train 30 seconds after start, exactly this line was perpendicular to this line of motion. This angle is 90 degrees. Now we know that this is the time where the event 1 is taking place, this is the point where the event 2 is taking place, and the distance between them we have just calculated is equal to this much. Now the train travels from this point, which is event 1, to this point, which is event 2, in how much time? 30 seconds, or in fact 60 seconds, not 30 seconds, 60 seconds. And if we want that, we are trying to find out a reference frame for which this particular event 1 and event 2 will happen at the same point, it's obvious that the car will have to also travel this distance, which is equal to 240, in a time which is equal to the time difference between event 1 and event 2. So in other words, this car will have to travel 242 meters in 60 seconds. Right? So if it travels at constant speed, its speed will be equal to 242 by 60. Right? So this will ensure that the car, as it goes in this direction, the way it is at this point, when the event 1 has happened and the train is at this point, the car will be exactly here, and when the train is at this point and when the event 2 has happened, car will be exactly at this point. So the distance traveled by the car in these 60 seconds will be the same as the distance traveled by the train in these 60 seconds, and that will be equal to this much. So in that case, it will seem from the car, for any person who's sitting inside this car, that event 1 and event 2 have happened at the same point. Right?